Okay. Okay. So we have been talking about the finite difference method in the previous class, and if you recall, we had taken the transient 1D heat conduction equation. Okay. So if you recall, 1D transient heat conduction. So if you recall, what we have done, that if I write this left hand side for ith node as Ti plus 1 minus 2 Ti plus Ti minus 1 divided by delta x square at time level n, and in the right hand side I will be having 1 by alpha at point I into T I at n plus 1 minus Ti at n divided by delta t. So in this way, whenever we will be solving, one more, that MS student is also not there. Anup, please call him as well. So in this way, what we will be getting, we will be able to calculate Ti at time level n plus 1. Is this point clear? So in this approach you can see that we need not to solve the equation because all other parameters are from the previous time level. So obviously the things will be already known to us from the previous time level. So we can calculate this one single unknown parameter in this equation at next time level n plus 1. So this type of approach is called as explicit approach. Okay. We are getting the value of the variable at each node point because we already know the value of other variables at the other node points. Okay. Now there can be one another approach where instead of writing this left hand side at time level n plus 1, we can write this at the same time level where we are actually doing the calculations. Okay. So in this way, what we will be getting, Ti plus 1 at n plus 1 minus 2 Ti at n plus 1 plus Ti minus 1 at n plus 1 divided by delta x square, and this will be equal to 1 by alpha I times Ti at n plus 1 minus Ti at n divided by delta t. Okay. So now you can see the left hand side, each and every parameter we need to estimate at time level n plus 1. Okay. So in this way, what will be happening? In this way, you can see that this is a single equation. Okay. And in this single equation, how many unknowns are there? T I plus 1, because all the parameters which are at time level n plus 1, these are unknown. So at time level n plus 1, we have one at I plus 1th node, at ith node, and I minus 1th node. So in this way, how many unknown parameters we are having? 3 unknown parameters, and we have a single equation, okay, for a given node point. So it means that in this approach I will not be able to determine the value of the unknown parameter from this single equation. All are clear with this idea? So now what we will do here, we will slightly try to simplify it. So I can write this alpha delta t by delta x square on left hand side, and let me consider this entire quantity as some constant a. Okay. So if I consider this some constant a, then I will be getting that a times Ti plus 1 at n plus 1 plus Ti minus 1 at n plus 1, and you can see in the left hand side we have one Ti at time level n plus 1 and this Ti at n plus 1. So this, if I bring to left hand side, I can take minus outside, it will be becoming 1 plus 2a times Ti at n plus 1, and in the right hand side I will be simply having minus Ti at n, which is a known parameter. Is this one clear? So this is my now generic equation. Now if I write this equation for second node, then for I equal to 2, it will become a times T3 plus T1 minus of 1 plus 2a times T2 at n plus 1 equal to minus of T2 at n. What I will be getting for third node? I equal to 3. A times T4 at n plus 1 plus T2 at n plus 1 minus of 1 plus 2a into T3 at n plus 1 equal to minus T3 at n. Okay. Likewise, for each and every internal node points, I can write the equation. Now, all these equations will be now forming a system of equations. Okay. So, in this system of equations, what I will be getting? This will be my coefficient matrix. Then I will be having unknown vector. So, unknown vector will include T2 at n plus 1. Then, because T1 at n plus 1 will be already known to us, or let me include it like here only. So, all these are the parameters which are at which time level? N plus 1. Okay. Now, what is my first node? First node is a boundary node. Okay. So, at boundary node, I will be having the known boundary condition. So, because of the known boundary condition, at first node, I will be simply writing one coefficient over here, which will be multiplied with this, and this will be equal to boundary condition value T naught. All are clear with this point? And all other coefficients will be 0, 0. Then when I will be going for the second node, now what I have in second node? T1 is multiplied with A. So A will be the coefficient. Other coefficient will be T2 is multiplied with minus 1 plus 2A. So second coefficient will be minus of 1 plus 2A. What will be third coefficient? T3 is again multiplied with A. So A. And all other are 0, 0, 0. And in the right hand side, I will be having minus of T2 at time level n, which will be a known parameter because it is at the previous time. When you will be going for the next equation, what you will be getting? A minus of 1 plus 2A, then A, and in here minus T3 power. Likewise, I will keep on moving till I get the final node, say TL at n plus 1, which will be having temperature value equal to TL because of the boundary condition. All are clear with this point? So now if you see, whenever individually I am looking for the equation at a particular node, then in that particular equation the number of unknowns were large. Okay, so in comparison to number of equations available. But simultaneously, whenever we have seen the complete system of equations, then number of equations and number of unknowns have become equal and the system of equations is determinate. Okay, so this way when I am calculating my solution for all the variables using the complete system of linear equations, this type of approach is called as implicit approach. Okay, all are clear with this idea? Now you can see in both these approaches, our left hand side, which was the diffusion term, this diffusion term is obtained using the central difference scheme. Okay, and this central difference scheme is actually second order accurate. But this right hand side is calculated using the forward difference scheme, and this scheme is nothing but first order accurate. So you can see the one side is having higher order of accuracy and other side is having lower order of accuracy. So typically in a system, if you are solving using the higher order but any one term or any one nodal value is estimated using the lower order of accuracy, then ultimately the benefit of higher order of accuracy is actually compromised. Okay, so we do not get the full benefit of using the higher order accurate terms. So ultimately there can be attempts to increase the order of accuracy of this time term. So one point is very clear to us. I cannot apply approach like central difference scheme in case of this time term, because ultimately in time I cannot move to the past. I have to start from the present and then predict the next time level. Okay, so I have to approach in the forward direction only. So that's why what is done, basically one another approach was proposed by Crank and Nicholson, and based on this approach, what they suggest that we can determine the value ti n plus 1 minus ti n divided by delta t. It can be written in terms of alpha times 0.5 ti plus 1 n minus 2 ti n plus ti minus 1 n divided by delta x square plus 0.5 into ti plus 1 n plus 1 minus 2 ti n plus 1 plus ti minus 1 n plus 1 divided by delta x square. So what they have done, in the right hand side, whenever we have to calculate the complete quantity, that quantity is estimated by using the half weight. Okay, half of the weight is given to the previous time level and half of the weight is given to the next time level. Okay, so equal weightage is done. So in this way, if you try to further resolve this equation and represent it in terms of Taylor series expansion, you will be finding that in terms of time also the order of accuracy will be becoming delta t square. Okay, so Crank-Nicolson approach is basically second order accurate in both time as well as space. Okay, so because diffusion parameter represents the spatial variation and the left hand side is representing the temporal variation. However, in order to calculate using this equation also, only this portion will be known and this remaining portion will be unknown. So ultimately you will be finding that overall this approach is also implicit. Okay, because you have to solve the way we have solved in the pure implicit approach. Is this point clear? So this is called as Crank-Nicolson approach. So mostly with this knowledge we can apply all the fundamental ideas of finite difference approach for solving our partial differential equations. Okay. Now after that, if you recall, I have given you idea about the scalar transport equation. Okay, so in terms of scalar transport equation, we have seen that del by del t of rho phi plus divergence of rho v vector phi equal to divergence of gamma gradient of phi plus s phi. So first term is temporal term, second is advective or convective term, third term is diffusive term, and final one is the source term. And how we do the physical interpretation of this system, that we have already studied. Okay. Now what I want to do, I want to show you the next approach, which is FVM, finite volume discretization. Okay, and while I will be showing you finite volume discretization, I will take the help of scalar transport equation to demonstrate you the idea of finite volume method. Okay, so typically what is done in case of finite volume method, your domain is divided into small volumes, which are called as, all these are called as control volumes. Okay, so these small volumes are nothing but called as the control volume. Now here also we can have two types of approaches. One is vortex centered approach and one is cell centered approach. So typically majority of the finite volume codes, you will be finding that these follow the cell centered approach. So typically what we have large number of these finite sized control volumes, and the center of the finite sized control volume stores the value. So this is the node point which stores the value of all the parameters. Okay, and at these node points, whatever the value we are storing, that is nothing but volumetric average representative of that cell. Is this point clear? Because whenever you will be considering a finite sized volume, so now there is the difference. One volume we define infinitely small, and second volume we define finite sized control volume in our basic fluid mechanics approach. Okay, so infinitely small control volume we define when we want to consider the variation of property at each and every point within the flow domain. That is, we want to use the continuous variation approach. On contrary, we use the finite size control volume approach when we go for the integral approach. Okay, so we consider a large size control volume. Over this we do integrate our governing equations, and from there we try to estimate the bulk parameters which are average representative for the complete system. Okay, so if you recall in basic fluid mechanics course, Reynolds transport theorem we use. So whenever we use the Reynolds transport theorem, we obtain the integral form of equations for a finite sized control volume. So that type of approach is used in case of finite volume method. Okay, because each of the control volume which we are defining, this is finite size. It is not infinitely small. Okay, so it is of finite size. So what we will be doing, we integrate PDE over the finite sized control volume. So once we will be integrating the partial differential equation, so ultimately whatever the parameters I will be getting, the parameters I will be getting will be representing the volumetric averaged quantities at the node points. Is this point clear? So now what I need to do, if I have to convert this scalar transport equation, which is a partial differential equation, if I have to convert this equation into algebraic equation using the finite volume approach, what I need to do first? If I have to convert using finite difference method, then it's very simple. Using the finite difference method, this is the first derivative. This del I can expand in the detailed derivative form, and then I can see whatever is first order derivative, then using the particular formula and using appropriate scheme, whether forward difference, backward difference, I can substitute all the derivative in terms of algebraic difference equations, and I will be getting a detailed equation. Okay, so finite difference we have already seen, but if we have to use the approach of finite volume discretization, then what I need to do? I need to first integrate this equation. Okay, so let me now integrate this equation over the control volume. So integration of first term del by del t of rho phi over the volume into dv plus integration over the volume of the second term. What is second term? Divergence of rho v vector phi into dv equal to integration of over the volume in right hand side. Okay, so divergence of gamma, what I will be getting? Gradient of phi into dv plus integral over the volume s of phi into dv. Is this point clear? All are clear with this idea? Now the first term, because I am using a fixed control volume, okay, and the size of the control volume is also fixed. This v is not function of time. Okay, so say if you use an approach in which at every time level your size of the control volume is changing, in that scenario this derivative term del by del t you cannot take out of the volume, because ultimately this volume is changing with time. But if I say that I am using a control volume which is fixed in the space and its size is also not changing with time, so in that case my limit of integration will be becoming independent of time, it is not depending upon the time. So ultimately, either if I take the time derivative of this quantity and then integrate over the volume, or if I first do the volumetric integration and then take the time derivative, both the quantities will be remaining same. Is this point clear? Because my limit of integration is not dependent upon time. So what I can do from the first term, del by del t I can take out of the integration. First I can perform integration and then I can calculate the temporal derivative. Is this one clear? Now in this way I will be using over here say integral rho phi into dv. Okay. Then plus if I am having one divergence term and its volumetric integral is done, if I have to write this in terms of surface integral, how I can write? Using Gauss divergence theorem. Okay, so we all know that Gauss divergence theorem tells that if we are doing volumetric integral of a divergence quantity, then that quantity can be written in terms of area integral, and divergence will be, del operator will be avoided, and along with this we have to consider normal unit vector and area, because we are integrating it over the outward normal. Is this point clear? So the conversion from this term to this term is based on the which theorem? Gauss divergence theorem. Is this point clear? Now after this, what I will be doing? Right hand side. In the right hand side again I am having the del operator here. So here again I will try to apply the Gauss divergence theorem. So if I apply Gauss divergence theorem, I will be getting area integral. First del will be gone. Gamma times gradient of phi dot n cap into dA, where n cap is the outward normal unit. All are clear with this idea? Now let us consider that the integral of s phi. So s phi means it's a source term. Okay. So source term will be having different values over the different portions of the volume. Okay. Now to incorporate this, I will be doing the volumetric averaging of this quantity. So let us consider after doing the volumetric averaging of the source term, I am getting some volume averaged source term S bar phi over here. Okay, so this is nothing but my volume averaged source term. Okay. Ankit, you can call one more guy is left. Ajay. And Ajay and Anoop. So this is the source term over here. Okay. So now what I will be getting from the first term? Now first term is actually interesting. What you will be doing over here in the first term, let me multiply with volume and let me also divide with volume. Okay, so what I have done, I have multiplied and I have also divided with the volume. What does it represents? Only this much portion. What does it represents? It represents that rho phi we have integrated over the volume, and then finally we have divided it with the total volume. So ultimately this integration will give me the volumetric average representative quantity. Is this one clear? All are clear with this idea or not? Okay, so ultimately, say this is the room, this is our finite size control volume. In this room, if you say that at this point some value of phi is different, at this point it is different, at different portions of the room the value of phi is different. Now ultimately, if I do the volumetric integration of all the values of phi and then divide by the complete volume, then what I will be getting? Volumetric averaged quantity. Okay, so from this integration, if I do multiply with v and divide with v, ultimately I can say that this entire quantity can be written in terms of rho phi bar. Is this not clear? Where phi bar is, even rho also I need not to consider, I can directly write it in terms of phi bar. Okay, so here phi bar, what phi bar will be? Or let me consider rho, that will be ease for understanding it further. So what phi bar is representing? Now phi bar is representing the value of this property at which point? Node point. All are clear with this idea? So at different portion of this cell, the value of phi can be different, but we are not interested in values of phi at different portions of the cell. Ultimately, whenever we are using the finite volume approach or numerical approach, our interest is to calculate the value at the node point. Okay, so node point over here is at this location, so I need to specify the value for node point. So once I will be defining for node point, I am interested in average representative value phi bar. Is this one clear? So after doing this first step, the first term can be written in terms of V I have multiplied into del by del T of rho phi bar. All are clear with this idea? Now what about second term? This is the second term. What does it represents? It represents rho phi v vector dot n cap d and integration over the area. So typically the mathematical meaning of this is, if I am having any arbitrary control volume, I am calculating how much rho v phi is passing through this outward normal boundary. Is this point clear? That is the corresponding physical meaning of this particular mathematical term. So ultimately, over the entire boundary of the control volume, I am doing the integration. Is this point clear? Now, if you see the finite volume method which I have defined over here, the finite volume or control volume. So in this control volume, I am having how many boundaries? One is this boundary, other is this, third and fourth. So in this control volume, so whenever I am having curved control volume, it is difficult for me to identify the number of control volumes, number of control surfaces. But in this type of particularly defined control volume, easily I can find the number of control volume boundaries. Okay, so as the number of boundaries are clear to me, and of course in each boundary I can define the normal direction of velocity easily, which will be used to calculate rho v vector phi across this boundary. So what I can do, instead of using the integration over here, I can easily substitute this integral in terms of summation over all the faces of the control volume and simply rho v vector phi into area of a particular face. Is this point clear? So now this integration I have converted into the corresponding summation sign. And what is the reason for converting into summation sign? What does integration represent? Integration basically represents the summation over small elemental areas. Okay. If I can easily define the number of elemental areas, elemental boundaries present in a control volume, then I can simply do the summation over all the boundaries and that will be becoming my complete area integral. Is this point clear? So this way, this term I can write in terms of rho v vector phi into area of a particular face when I am doing integration over all the faces of the control volume. Is this point clear? Now what I will be getting? In the right hand side again I can write it in the similar way. So summation over the area and gamma gradient of phi into area. All are clear with this point? And of course last term already we have got some volume representative quantity as per phi. All are clear with this idea? Now, first term is temporal term and this term I have to write in terms of the algebraic expression. What about second term? Is it still a derivative term or is it now algebraic term? Second term is now an algebraic term. Why algebraic term? Because if I consider a two-dimensional control volume that will be having four faces, say this is east face, west face, then north face and south face. I have to calculate what is the meaning of summation of rho v vector phi dot af. The meaning of this is value of rho v vector phi at east face plus west face plus north plus south face. Okay, and none of the terms involved in these individual values, individual terms is having derivative involved. Okay, so this is nothing but a now algebraic term. But what about the third term? Third term will be becoming gradient of phi into AF. So this quantity is still having one derivative term. So ultimately this derivative term we have to also approximate. Okay. So this derivative term we can easily approximate with the help of interpolation functions. And after replacing this derivative term with the help of interpolation functions, what I will be finally getting? I will be getting a algebraic, all the terms in my equation will be algebraic equation, and this equation then I can apply for each and every node point in my domain. Okay, so the further extension of this equation with the help of an example I will show you in the next lecture, and we will stop for today.